Hi everyone. Today I'd like to continue our discussion of quantum mechanics in three dimensions. Last time we introduced this subject and we focused on the problem of a particle in a rectangular three-dimensional box. All right? A problem with Cartesian symmetry. Well, this class I'd like to focus on central force problems, problems that have spherical symmetry. In these problems, the only force acting on our particle points in the radial direction. All right? These are interesting because there are a lot of physical systems that behave like central force um, problems, all right, that can be modeled as central force problems. And the most important one, which we're coming up to pretty soon, is that of the hydrogen atom. Anyway, I'd like to go ahead and get started. Let's turn to the notebook and have a look at an outline. All right. So as I mentioned last time, we talked about quantum mechanics in 3D and introduced the particle in a 3D box problem. All right? And I'd like to quickly recapitulate what we found. But then we're going to go on and focus on central force problems. First, we'll define what a central force problem is, but then we'll turn to examine this with quantum mechanics. In order to do this, we'll see that we have to write Schrodinger's equation in spherical polar coordinates. And we'll talk about how that works. It makes things a little bit more complicated, but these problems turn out to be much easier to address in spherical coordinates and Cartesian coordinates. Once we've done that, we'll look for separable solutions to Schrodinger's equation, because those are the ones that will describe these highly symmetric problems. Okay? We'll find that the angular part of the wave function can be described with functions called spherical harmonics. And we'll see that states like these uh, exhibit quantization of angular momenta. So quantization of angular momentum. Then we'll look at the radial part of the wave function. And then the final thing I want to do is to look at an example of kind of the simplest possible central force problem, which is called the rigid rotor. All right? So that's what we're going to do. Here, I'd like to quickly recap what we learned about the particle in the 3D box. Okay, so we examined this problem last time as our first example of a three-dimensional quantum mechanics problem. In this case, the wave function for our particle depends on all three coordinates, x, y, and z. So in Cartesian coordinates, psi is a function of x, y, and z. All right? And we can write Schrodinger's equation in three dimensions. Here, I'm going to move this equation down. I think I need a little bit more space. There we are. So, minus h bar squared del squared psi equals energy minus potential energy times psi. All right? And here, del squared psi can be written in Cartesian coordinates very simply. It's second derivative with respect to x squared plus second derivative with respect to y squared plus second derivative with respect to z squared acting on psi. All right? For this problem, we found that the wave function, that the solution, the wave functions that solve this problem are in separable form. The energy states are in separable form. That means that they can be written as a product of one function that depends only on x, one function that depends only on y, and a third function that depends only on z. Okay? And by substituting this back into Schrodinger's equation and turning the crank, we found our results. All right? First, we found an expression for the wave function, which I'm going to write out here. Oh, I'm going to run out of space for sure. Okay? There we are. There's a normalization constant times sine nx pi x over L times sine ny pi y over L times sine nz pi z over L, where nx, ny, and nz are the quantum numbers for this system, and they each take on integer values. Additionally, we found that the energy levels for this system were given by uh, h bar squared pi squared over 2ml squared times nx squared plus ny squared plus nz squared, as I'm sure you remember. Okay? If we use a shorthand where the term in the parentheses here is called E0, we use that same shorthand for a couple of different systems, so be careful. Then we can sketch out these energy levels kind of simply. So the lowest state would have nx, ny, and nz equal to 1, and that state would be at an energy of, using this notation, 3 times E0. Okay? The next state turns out to have nx equals, say, 2, and then ny and nz equal to 1, and that has an energy of 6 E0. The next state might have an x equal 2 and y equal 2 and z equal 1, and that has an energy of 2 squared plus 2 squared plus 1, or, oh, I'm sorry, 9 E0. Okay? And continuing this, second. We get further energy states as shown. One of the interesting things about this is that the states can be degenerate. If we look at the ground state, there's only one state, so that state has a degeneracy of 1. But if we look at the next state, which we've shown here as 211, well, there are two other states that have the same energy, 121 and 112. Taken together, they have a degeneracy of 3. There are 3 states with the same energy. The next state also has degeneracy of 3, as does the next. And then the following state, 222, has a degeneracy of 1. Okay? And one can figure out the energy and the degeneracy of all the other states that one might want to think about by continuing this series. But this phenomenon of having multiple states at the same energy, it's a facet of three-dimensional systems, and it doesn't occur in one-dimensional systems. All right. Well, that's what I wanted to remind you of to help us get started with our discussion. But now we're going to continue by talking about central force potentials. So I think we'll stop this video here and take it up in the next.